Hello, grade 11s. Trig is the gift that keeps on giving. And so we start today with a new topic. We've spent a lot of time on reduction. So that was topic 3, and it spanned a whole series of subtopics. And now we're starting topic 4, which is trigonometry identities. So trig identities are an awesome topic. And what's quite nice is that the two trig identities which we're going to learn, you're going to say, oh, but I've seen that before, because we've been sowing the seed this whole time. So this video is going to be on an introduction to trig identities and some of the easier examples. And then in the next lesson, we'll go into the more complicated examples of trig identities. So by the time you're in matric, you learn quite a few trig identities, but in grade 11, we focus on just 2. And the first one is the idea that sine squared of an angle plus cos squared of the same angle. So most importantly to notice that you've got theta and theta. You can't have different angles. But sine squared and cos squared of the same angle always land up at 1. Now the important thing is going to be that we can prove this. They never ask us to prove it generally in an exam, but it's nice to see why this occurs. Now it's actually a really simple proof. So if we start at sine of theta, by definition, sine of theta is y over r. If you're thinking of a Cartesian plane, you could say it's opposite over hypotenuse, but if I want to make sure that this is true for every angle, I'm going to use the Cartesian plane definition. So basically y over r squared. And then we have cos of that same angle, and cos by definition in the Cartesian plane is x over r, and you're going to square it. So basically this is equal to y squared, because remember when you square a one term, you're allowed to distribute the square only when you square one term. So this is y squared over r squared. And the next term is x squared over r squared. Now you'll notice that means we're adding 2 fractions. And these fractions have the same denominator. And when fractions have the same denominator, you are allowed to simply add the numerators. So I don't actually have to do an LCD here, because the LCD is done for me. My common denominator is r squared. So my top is, okay, now I don't know out of habit I'm writing x squared first, but you can write it as x squared plus y squared, or I could write it as y squared plus x squared, because remember order does not matter for addition. And basically, what is x squared plus y squared? X squared plus y squared, or y squared plus x squared, if you use Pythagoras, if you go back to all those Pythagoras examples that we did, by Pythagoras, x squared plus y squared is r squared. So this is wonderful. So I get r squared over r squared, which is always 1. So by Pythagoras, this is equal to r squared. So pretty nifty, that little proof. It's not particularly difficult to follow at all, and it's fairly simple. Okay, now the only thing I need to add on to this is we must remember that if you have something which is true, so if you have sine squared plus cos squared is 1, we can manipulate that to write it in different ways. So there's actually 3 ways of writing this identity. First of all is the way I have given to you, so sine squared plus cos squared is 1. Secondly, you could take your cos squared over, that's a terrible way to say it, but you can isolate your sine squared. So you could say, if I want to isolate sine squared, I'm going to subtract cos squared on both sides. So I'm going to get 1 minus cos squared of theta. And lastly, what happens if you wanted to isolate cos squared of theta? Then I could minus sine squared on both sides, and so I would get 1 minus sine squared theta. So actually sine squared plus cos squared is 1, but that can morph into 2 other ways of looking at that identity. So you've almost got to think of this as 3 kind of identities packaged into 1. Okay, so that's kind of the first identity which we need to remember. And the second identity we have spoken a lot about, because it came a lot into our reduction questions. And that's the idea here that tan of an angle can always be rewritten as sine of that angle over cos of that angle. And the reason being, if I start with what is sine of theta divided by cos of theta, what does that mean? Well, first of all, I prefer to write it as sine of theta divided by cos of theta, and I'll show you why. Sine of theta by definition is y over r, which means I've got a fraction. So that's why I prefer to write it with the divide sign. And I'm dividing by cos of theta, which is x over r. Now, if I just think of, kind of grade 8 maths, how do I divide fractions? I tip and times. So I change that to a multiplication sign as long as I flip around this fraction. So it's r over x. Now, what most of us will notice is we can cross-cancel our r's, and so this simplifies to y over x. And voila, y over x is the definition of what tan is. So this simplifies to tan of the same angle. So again, actually a really nifty kind of short proof, but very cool and very, very useful. Now that's actually all the content I need to teach you for trig identities. The hard part, however, is applying these in the right places and figuring out where and how to use them. So we're going to look at a whole bunch of examples. We're going to start off with some slightly easier ones in this lesson. They do get fairly tricky already in this lesson, but they are such fun. So let's have a look at it. Examples. Okay, now a couple of really important things. This question always says prove the following identities. So what I mean by prove is you cannot assume that they are true. You have to prove they're true. Okay, so I've written myself that note there. I can't assume they're equal, and therefore you cannot have an equal sign. So there's not allowed to be an equal sign. So this is personally what I do when I answer a question. When it says prove the following identities in a test, I write myself the following. I say RTP. Now, I don't know if you remember RTP from geometry. RTP stands for required to prove. So I like to have on my sheet what I'm trying to show is equal. Then what I do is I write myself a little heading that says proof. Now, the moment you write proof, you can't have an equal to sign. And so what I do is I divide my page in half with a little line, and I write the left-hand side down and the right-hand side down. So here I have written down my right-hand side. My right-hand side of my identity was this long product. I've written that down, and then I've written down the left-hand side. Reason being, it's very important to see what you're trying to do. What am I trying to show? But you can't have an equal to sign, because at the moment these aren't equal, I'm trying to prove that they're equal. Now, the whole aim of this identity is to manipulate one of the sides or both of the sides till they eventually look like the same thing. So I've written myself that note there, and that's very important. I need to manipulate one or both of the sides until they're identical. Now, basically, there's no rules of what to do first. However, by the end of trig identities, we're going to have a couple of kind of like skills that are really useful in these things. And the first skill is apparent here. So the first thing I do in every single identity is whatever side has a tan on it, I go and rewrite what tan is equal to. Because ultimately I can't really work with tan. I want to work with sines and coses, so maybe things can cancel. And so my first skill, which we're learning in this example, is always replace tan with sine over cos. Okay, so I've written myself a note on that skill, and that's a really important one. So what I do is I can immediately see that the left-hand side is quite messy, and it's got a tan. So I'm going to start there. Now I'm allowed to put an equal sign because all I'm doing is I'm arguing that this first line is equal to the next line. You're just not allowed to put an equal sign between the two lines. So if I do what I have suggested, and I replace cos of theta with, tan of theta, with sine of theta over cos of theta, and you can just replace, you don't have to give a reason or anything, that is an identity which we are all meant to know. Now what happens here, which is quite beautiful, is that the coses cancel, and so what do you know, the left hand side simplifies down to sine theta times sine theta, which is sine squared theta. So in this case I now have the left hand side, which is sine squared, and the right hand side is sine squared, which now means the two sides are equal. So in this case, I didn't have to manipulate both sides. So then I'm going to say, therefore, my left-hand side equals my right-hand side. And the moment that is happening, you have proved that this identity is true. Right, so all these examples are going to do to us is basically teach us skills and allow us to practice the skills that we're developing. So next thing which we're trying to prove. So in an exam, I would write required to prove, and I would write proof, and I would draw a line down the middle of my page. Right, so I've written my left-hand side down and my right-hand side down, and my rule of thumb is start with the side that's messy. Start with the side where it looks like I can do something. So if I look at the right-hand side, it says cos x. Well, that's very boring. There's no tan x, there's nothing there for me. If I look at the left-hand side, that's definitely messy, and I'm like, I don't really know where this is going to disappear to, but I want cos x, and I've got cos cubed and all these things. And so this brings our second skill in that we need to always remember when we're working with identities. And that second skill is never be afraid to factorize. Factorizing is a huge skill that we use in identities. So the moment I look at this and I'm like, hang on, this is one term on the right-hand side, and the left-hand side is two terms. What's the only way to make two terms into one term is to factorize. So what can I factorize here? Well, here's a cos cubed in this term, and here's a cos x. So cos x is a common factor. Now, if this factorizing freaks you out because it's trig and factorizing all in one, let me show you a bit of a trick. Think of this as kind of the same as a cubed plus a times b squared. That's pretty much what's going on here. If you think of cos x as a, this is a cubed, and then this is a. And then you can see that a is clearly a common factor. You can also see that you would be left with a squared. If you took out a, you'd be left with a squared plus b squared. Now, I'm actually not working with a's and b's, but that's the idea. So if I'm struggling, I can realize that this would be a squared, so this is cos squared x, and then this would be b squared left behind, sine squared x. And what do you know? Oh my word, cos squared plus sine squared is 1. So basically, this is equal to cos x times 1, which is cos x. Now that's wonderful news, because now my left-hand side looks exactly like my right-hand side. So therefore, my left-hand side equals my right-hand side, and this is proved. So this is an example of where the one identity came in, but we had to factorize in order to help us get there. Right, on to the next one. Required to prove, and I'm going to do my proof. I'm going to divide my page in half and write down my left-hand side and right-hand side. Okay, now that I've done that, this is where things start to get a bit messy, because there's so many things that you could do. So I'm definitely thinking to start on the left-hand side because it's super messy, and I see a tan, and the first skill I learned was let's replace tan. I also start to think, should I not be multiplying out? I mean, I could go this and I could multiply out, and there's nothing wrong with that. But once you get really good at this, you start to see some patterns. So the pattern I see here is, hang on one moment, there's 1 and a minus sine squared. And have a look out for that. The 1 and the minus sine squared, or the 1 and the minus cos squared. Try and look out for that. So I'm not going to multiply out just yet. I'm going to realize that 1 minus sine squared is the same thing as cos squared theta. So have a look out for that identity. So actually, I am going to need to multiply out, but I don't have to do a binomial times a binomial. Try and avoid complex multiplying out if I can. So first I noticed my identity of 1 minus sine squared is cos squared. Now where did that come from? If I just scroll up here, this is from the fact that this identity can be manipulated in two different ways. And so you do get much better at this over time, and you get used to seeing these things and you pick up these patterns. Okay, now my first skill was always change tan. So this is tan squared, not a problem. Tan is sine theta over cos theta. So this is just sine squared over cos squared. So personally, before multiplying out, I would change my tan, only because if you have a look at what's going to happen here, I am going to multiply out, and guess what? I think the cos squareds are going to cancel. So when cos squared times 1 is cos squared theta, but when I multiply this cos squared by the second term, my cos squared with my cos squared will cancel, and I'll simply be left with sine squared theta. And what do you know? There is that 1 again. Sine squared plus cos squared, or vice versa, is 1. And so my left-hand side and my right-hand side are absolutely identical, and so I have proved this identity. So again, we learned, what we used here was skill number 1. We changed tan. Then the other 2 were just identities that we were looking for. Okay, so I've just written 2 more skills there. The first skill there, number 3, was look for the 1 minus sine squared and the 1 minus cos squared, or the sine squared plus cos squared. Just be aware of those. And then skill number 4, multiply out when you need to. If you're at a point where you have a product and you don't know what to do, multiply out. See where it goes. Right, let's look at another one. We are required to prove 1 minus cos squared over 1 minus sine squared is tan squared, and we're going to start with our proof. So, line down the middle. So I've written my left-hand side and right-hand side, and now you'll notice the left-hand side looks messy, but the right-hand side has a tan. So often what I will do here is I personally like to change my tans, even though this is on the right-hand side, because then it gives me a kind of goal as to where I'm going. So that's my goal. This apparently has to somehow equal to sine squared over cos squared. Remember, tan is sine over cos, and if you square the tan, it just means both of them are squared. Now there's nothing much more I can do with the right-hand side, and so now I'll turn my attention to the left-hand side, and I'll say to myself, right, how can I change this? Now what's wonderful is that because you've manipulated the right, it gives you a good idea of where you're trying to get to. And so all of a sudden you do recognize, hang on, 1 minus sine cos squared is sine squared. That's the identity, one of them that we learned. And hang on, 1 minus sine squared is also cos squared. And so I actually just need to manipulate both sides, and they're actually now equal to each other. Now there's nothing wrong with then saying, oh gosh, this is tan squared, and then you don't have to do that. So you don't have to manipulate both sides. You could have just manipulated the left. Personally though, I'm going to erase this because I like to know where I'm going towards, and so I like to change tans. Right, so therefore my left hand side equals my right hand side. Great, on to the next one. So required to prove, and my proof. I'm going to put my line down my middle so I don't get tempted to make these equal to each other. Right, so let's look at these things. Let's look, they both look equally messy. Now just to point out, this is a minus sign. So because it's not a plus sign, that's not 1. Sine squared plus cos squared is 1, and there's no identity with sine squared minus cos squared yet. In grade 12 we do look at a version of that, but that's not sine squared plus cos squared. So if I look at my skills, I personally immediately look for tans. There's no tans. There's no products. There's no fractions. There's nothing. And so what's that other skill that we learnt when we were like, okay, well, there's nothing to do? We learnt about factorizing. Now notice this is sine to the power of 4 and cos to the power of 4, whereas this side is sine squared and cos squared. So possibly I need to factorize. Now my first type of factorizing is a highest common factor, and I don't see a highest common factor. My second type of factorizing is dots. Now let's just look. I could think of this as a to the power of 4 minus b to the power of 4. Now is that a dots? Yep, that's a dots. So if you're struggling to factorize, put letters like a and b in and then factorize. I know that this would factorize to a squared plus b squared and a squared minus b squared, which is looking very promising. So what does this actually factorize to with sine and cos? This will be sine squared theta plus cos squared theta. Now immediately I write that down. I'm like, oh, isn't sine squared theta plus cos squared theta, isn't that 1? And this is exactly what happens. That is the identity of 1. And so I get 1 times sine squared theta minus cos squared theta, which is exactly what I wanted, because that is on the right hand side. So I'm going to erase my A's and B's because that's not what I would have in a test. I would scribble that on my question paper if I'm struggling. And there we go. Pretty nifty. So therefore, my left hand side equals my right hand side. And notice that factorizing comes up again. It's a really, really useful skill. Right. Couple more to go. Required to prove. And that's what I'm required to prove. So I'm going to start with my proof and write down my left hand side, right hand side. and divide my page in half. Right, so I've written down my left and my right, and the left-hand side looks messy, but the right-hand side looks equally bad. But my attention is drawn to the right-hand side because there's tans. If I look at the left-hand side, there's no tans. I suppose I could try and factorize, but the moment I see tans, that's my starting point. So I'm going to abandon the left side for now. I might come back to it, but I'm going to manipulate the right-hand side. Now you'll notice that tan is a fraction, and this is within a fraction. So I'm going to prefer to use my divide symbol. So tan of theta is sine of theta over cos of theta. That's the top of this fraction. And I'm dividing by 1 minus tan squared. So this will be 1 minus, and this will be sine squared theta over cos squared theta. Okay, now this is probably the most difficult example we've done so far. This is quite a nice one. Where to go now? And this is the next skill on our list. And this skill is, if you see two terms, we like to combine those terms. Because if you look at the left-hand side, there aren't multiple terms. Everything's one term. So I'm going to combine terms. If I have two fractions added together, I'm going to combine them, which basically means I need to add together fractions. And how do I add together fractions? I need an LCD. Okay, so I've written down the rest of the right-hand side. I just want to work on this bracket for the moment. If I'm going to create an LCD, I need to know what the denominator of the 1 is. And the denominator of 1 would be 1. Now, what would my lowest common denominator be? Well, the lowest common denominator is between 1 and cos squared. So my LCD is going to have to be cos squared theta. But that means that this 1 needs to be multiplied by cos squared theta to become the LCD. And what you do to the bottom, you do to the top. So I'm basically multiplying both of the bottom and the top by cos squared. So that becomes cos squared theta. Now just look at that for a moment. Cos squared theta divided by cos squared theta is 1. So I have basically converted 1 to a denominator of cos squared theta. Now I don't have to do anything to the sine squared over cos squared because that already had the LCD. Now, as you go along in identities, it's very helpful for you to always pause and go, do I think I'm on the right track? Now, have a look here. I see cos squared theta minus sine squared theta. And look what I see there. So always just check in with where you're trying to go towards. This is why I always write down both sides. Always look at where you're going. This is looking very promising. And so I'm going to continue. Okay, now how do I continue? Another skill is to remember how to divide fractions. Tip and times. So I'm going to multiply as long as I write the next fraction flopped around. So cos squared will be at the top, and at the bottom, I'm going to have cos squared theta minus sine squared theta. Now again, look at where you're going. This is good. That's exactly what I want. Tick. There it is, tick. I want the top to be sine theta cos theta. So this sine theta makes sense. This denominator of cos theta does not make sense. It's got to go. And have a look. That looks entirely exactly what's going to happen. Because one of these cos thetas is going to cancel with one of them there. So we don't actually want to scratch things out because the person marking needs to be able to see what we've done. But in theory, I'm cancelling one of the cos thetas at the bottom. So I'm going to have sine theta only in that fraction multiplied by only one of the cos thetas all over, because when you multiply fractions, you multiply tops and you multiply bottoms, and that cos theta is now gone. So I have cos squared theta minus sine squared theta at the bottom, which is exactly what I wanted. So one of the cos is cancelled. Therefore, my left-hand side equals my right-hand side. Now that left-hand side looked horribly messy, so I thought I was going to have to do something with it. But in this case, the right-hand side needed all the manipulation. Now this particular example is a perfect exam question example. It's fairly mean. So just to recap, we changed our tans, and then this new skill of ours which we've identified. If you have multiple terms, use a lowest common denominator and combine those two terms together. And then tippings and timesing, very useful, tip and times. And this idea of adding fractions together actually comes up a lot. Really, really nice question. Right, 2 more to go. Now this one looks very, very similar. So actually, why don't you hit pause and actually try this one on your own? Because this is seeming very, very similar to the previous question. I see tan squareds. That's looking like I could probably use the skills I already have in order to do this. So why don't you hit pause, try this one, and then mark it. Okay, I hope you've done just that. So how hopefully you've done this is to realize, hang on, I've got tan squared. So first of all, I'm going to rather write this as a division, and I'm going to change tan squared to sine squared over cos squared. So that's why I did my division sign, so I didn't have fractions within fractions. Inside the brackets, I have 1 plus sine squared over cos squared. And so our first skill has been used. Did we change tans to sines over cos? And now my second skill is to go and check this bracket and make it one term. So this has to become one term. So if I keep the rest the same and I just work on this bracket, you'll notice it's almost exactly the same idea. I am going to have an LCD of cos squared, which means I need to rewrite everything with an LCD of cos squared. So I must multiply that denominator by cos squared, which means I must multiply the numerator by cos squared, and I get cos squared theta plus sine squared theta. But what do you know? Cos squared theta plus sine squared theta is 1. So if I'm going to tip and times, I'm going to do this one step at a time, but basically I'm going to times by and I'm going to swap this round. So this is cos squared theta over. Now, cos squared theta plus sine squared theta is 1. So you could just write 1 here. If I just take it a little bit slowly, I'm now going to say that this is 1. And if you have a look, my cos squareds cancel. So this basically, I'm just left with the sine squared, which is exactly what I wanted. So therefore, my left-hand side equals my right-hand side. So skills we used here, we changed it to a division sign. We replaced the tans. We combined the fractions using an LCD. We tipped and times, and we used the identity of 1. Again, a fantastic exam question. Okay, and lastly, this one's slightly different, simply because I'm requiring to prove, and I notice what I'm requiring to prove. I didn't actually tell you what you were requiring to prove. Apologies, I mistyped that. I'm required to prove that this fraction is equal to 1. Now this is only slightly different because we've been working with thetas and now we have numbers, but it's no different really. I'm going to do it in exactly the same way. Right, so I've written down my left-hand side and my right-hand side. Now, interestingly enough, I see sine squared, and so I'm thinking sine squared plus cos squared is 1. But notice this is 70 degrees, and this is 20 degrees. Or to notice that this is also sine squared, and this is sine squared. So it's not quite sine squared plus cos squared, but I'm hoping after all our co-ratio examples, isn't 70 degrees plus 20 degrees equal to 90 degrees? Now remember, if two angles have this relationship, they complement each other, then they are related through co-ratios. So basically, I need to try and rewrite 20 degrees as something to do with 70, which I think I'm going to be able to do, because I think I'm going to rewrite this as 90 degrees minus 70 degrees, because then I can reduce it to a ratio of 70. Now if I look at the bottom, I'm seeing a similar idea, in that I'm seeing 40 degrees there and I'm seeing 50 degrees there. Now, those are related. So I think I'm going to want to change this 40 to 90 minus 50. Now, why have I targeted the 40? Why not target the 50? Simply because this is tan. And when we did co-ratios, we only really spoke about the fact that sine, if you're working from 90 degrees, changes to cos, and cos changes to sine. We never wanted to do a tan with a co-ratio because we don't study its co-ratio anymore. And so that's why I'm going to rather change the 40 degrees. Okay, so I'm going to give myself some space. So this is going to be sine squared 70, just because that came first. And I'm going to rewrite 20 as sine squared of 90 minus 70. So 90 minus 70 is 20. Now this is divided by, and I'm going to rewrite 40 degrees as 90 degrees minus 50 degrees. And then this is 1 plus. Now I know that there's a tan there, but because there's so much going on, I'm first going to do these reductions and then I'll worry about my tan in a moment. So this top becomes sine squared of 70, which was there. Now don't forget reduction. The first thing you ask yourself is, what quadrant am I working in? And 90 minus 70 is quadrant 2, so sine is positive. But I'm working from 90 degrees. So sine will change to its co-ratio of cos. So this is cos squared 70. And the moment I do that, I'm like, sine squared plus cos squared, that's good for me. Bottom, again, reduction. This is quadrant, so did I say quadrant 2? Sorry, clearly I was not thinking. 90 minus 70 is quadrant 1. My apologies. And the same thing in the bottom here. 90 minus 50 is quadrant 1. So sine is positive in quadrant 1, but look at me writing sine. If I'm working from 90, I change to its co-ratio, which is cos squared of 50 degrees. Now, simply because I've now kind of simplified that a bit, can I now look at this tan? This tan here, tan is sine over cos. So can I rewrite this as sine squared 50 over cos squared 50? Now why I'm doing that is because I'm quite well aware that I'm going to multiply this in the moment, and then my cos squares can now cancel. So I mustn't forget my 1 plus. So now we're pretty much almost there, in that in the top here, this sine squared of 70 plus cos squared of the same angle is 1. And if I look at the bottom here, I'm going to multiply my cos squared in, so that'll become cos squared of 50 degrees, because I'm multiplying by 1. And when I multiply it in the second term, you'll notice that the top is cos squared and the bottom is cos squared, so he's going to cancel. So I get plus sine squared of 50. And how beautiful is that? 1 cos squared plus sine squared is 1. So I get 1 over 1, which is 1. So therefore, my left-hand side is equal to my right-hand side. Now notice I probably should have said this at the beginning. I should have said without a calculator. Because if I don't say without a calculator, of course we could just go put that in a calculator. So in an exam, I would say without a calculator for this type of question. So that is a really, really beautiful question for an exam. So what have we done in this particular video? We have learned the 2 trig identities which we need to know. However, one of them morphs into like 3 different ones. And then all we've done is practice examples through which we've hopefully picked up some skills. So we now need to practice these basic skills. So our skills were change tan, factorize, combine fractions using an LCD, multiply out when you need to, things like that. So it's essential to practice this before we move on to some slightly more difficult ones.